So there's one other kind of regularization that we want to discuss briefly. Like we said, there's lots and lots of ways of regularization, namely lots of ways of avoiding overfitting or simplifying the space of functions that we're searching in. So dropout regularization is when in a neural network we add one or more dropout layers. Okay, what does this mean? Um, so you have the usual layers, and then you add another layer, a few perhaps, maybe after every layer, but maybe a few in particular um, dropout layers. What these dropout layers do is they set some fixed fraction of all inputs to the layer to zero, randomly selected set each time during training. What does this mean? So there's a dropout layer. There's a whole bunch of inputs coming into that layer. Um, all the dropout layer does is randomly selects, I don't know, 30% of these inputs and sets them equal to zero, and then lets the rest proceed unchanged. What this means is that, well, this dropout layer adds additional noise um, because it's randomly setting a few weights or biases to zero. But it also has the effect of making the trained model less overfit because the network cannot really rely on the exact values of the various parameters. Okay, um, because it cannot rely on the exact values of various parameters because there is a dropout layer, and the dropout layer might suddenly set one of the weights or biases to zero randomly. Because there is that possibility, the training of the network will proceed in a manner that the exact values of the various weights and biases do not really affect the output of the model to a particular input. This gives the model some robustness properties. Basically, like we said, the exact values of the parameters don't matter. Um, it makes the model robust to noise because this is the kind of noise that we're adding to the process that kind of makes it robust to some kind of noise in the data as well. Um, of course, dropout is only used in training. And once the training is done, namely like the initial optimization where you're finding all the biases and weights, and once the training is done, when you're actually wanting to use the neural network for some application, the already trained neural network, the dropout layers are dropped, they are ignored when you actually want to make a prediction for whatever purpose. Okay, so that's called dropout regularization. It's called a regularization because, again, it helps us from overfitting. Finally, I want to mention something called implicit regularization, um, which has to do with the properties of the stochastic gradient descent algorithm. Um, there's this word here, so I say modern state of the art, SOTA, in the machine learning world or maybe in the computer science world. The phrase state of the art is contracted to SOTA for some reason. Um, in any case, modern state of the art neural networks actually use lots and lots of layers and very large number of parameters, weights, and biases. Um, so the danger of overfitting may seem high, like we've discussed, and that's kind of motivated some of our discussion so far. But researchers over the last 5, 6 years discovered some remarkable thing, which is that just using the stochastic gradient descent for the optimization provides some implicit regularization. In other words, even though the neural networks could be very messy and overfit, um, the resulting functions have a certain smoothness to them. Um, and I'm not going to necessarily go into the theory of it. This is still an actively researched topic. There are people at Ohio State that are experts on this topic. And in fact, I heard a talk about this here about, I want to say about 6 months ago or a year ago. Um, Here's the basic idea. When the number of parameters in your network far exceed the number of data points, then there are infinitely many solutions that will have training error equal to zero exactly, right? This is like if you have 5 data points and you take a 10th order polynomial or something like that, the 10th order polynomial can go through all the points exactly, so fit the data perfectly, and uh, basically drive the training error to zero. Okay. So similarly, if the number of parameters in your neural network far exceeds um, the number of data points in some sense, then you can drive the training error to zero in principle. And typically, there are infinitely many solutions with training error equal to zero. Okay, there's going to be a space of solutions where the training error is equal to zero. And what people have found over the last few years is that among all solutions where training error equal to zero, the stochastic gradient descent actually picks up the solution with the least norm or sort of the smoothest function or something based on some metric, kind of like doing L2 regularization. Um, and this kind of property of stochastic gradient descent is called implicit regularization. Just using the algorithm, make sure that the function is not as complicated as it could be. Okay, because of this property, people have perhaps started skipping some of these uh, explicit regularizations like dropout regularization and so on. Um, anyway, so that's I just want to make a remark about implicit regularization. This is again, like I said, an active area of research.